My name is Stefan Janecek. I'm working at Unisoftware Plus and Math Consult in Linz in Austria. We are producing Unrisk, a financial risk management solution based on top of Mathematica. And well, in my second life, I'm still a theoretical physicist working with density functional theory calculations. And that also can be done in Mathematica, as I will present in my talk.
Hi, my name is Stefan Janecek. I work at Unisoftware Plus in Austria, and I'm going to talk about density functional theory in Mathematica. So before we jump right into the middle of things, let me briefly explain my motivation on the whole subject. This was in no way a commercial project. It was more like a hobby project generated by, well, basically by Wolfram's marketing on Mathematica 10 and the Wolfram language. So I realized I'm a pretty long time Mathematica user, but I've never used Mathematica as a software development tool or as a programming language. And the best way to learn a programming language is, of course, to do something slightly non-trivial with it. And I did choose density functional theory because I happen to be familiar with it, and it's not rocket science, but it's certainly not completely trivial. So a side benefit is probably, well, we are still doing a bit of density functional research together with Mike Eichinger, who is here in the audience. And Mathematica would serve as a nice platform to try out new ideas. As not all of you are physicists, I probably need to briefly explain what density functional theory is. I need to apologize towards the physicists. This is scientifically quite superficial, but just to give you non-physicists an idea of what all of this is about. So the dream behind the whole endeavor is that if you could solve Schrödinger's equation, which you see here, this would kind of hand you the keys to the kingdom of, well, most of chemistry, solid-state physics, semiconductor physics, material science, at least at the nanoscale. Oh, sorry about that. Hey, go away. And of course, if this sounds too good to be true for you, then this is because it certainly is. The problem is, this wave function that you are trying to solve for with Schrödinger's equation is a tremendously complicated object. And let me briefly show you how complicated it is. So this is a simple ethane molecule. It consists of 8 atoms, if I count it correctly, and 30 electrons. And 30 electrons would mean the wave function is a function in 30 coordinates, which amounts in 3D space amounts to 90 coordinate directions. And if you would naively discretize the wave function, and say take 20 grid points in each coordinate direction, you would end up with roughly that many bytes. So this is obviously a large number, but yeah, to give you a feeling of how large it is, assume you would have a future storage medium where you could store 1 byte per atom. This is probably as much storage density as humanity will ever achieve. This would allow you to fit 1 billion petabytes on the volume of a simple SD card. This is a lot of photos, actually. So how much volume would you need to actually store the wave function for ethene? Well, if you do the math, I did it with Mathematica, of course, it turns out to be roughly 10 to the 39th cubic light years. This is roughly, very roughly, 1 million times the size of the universe. Well, oh, this is this is really a lot. I hope I have convinced you that at this point, physicists are not just a lazy bunch of people. It's really, really impossible for probably forever to solve the many-body Schrödinger equation. Density functional theory is kind of one approximative way to at least go part of the way, and it's based on an astonishing theorem by Hohenberg and Kohn, who found out that at least all information about the ground state of this many electron system is actually contained in the density. And the density is a function in just one position. It's basically the probability to find an electron, some electron at this position. So this is a much, much simpler object. And my legalese here, it says in principle, because in practice you know that the information is in there, but you don't know how to get it out. So, and this is the place where you need approximations. The usual way it is done in practice is the so-called Konchem iteration scheme, where instead of this complicated many-body Schrödinger equation, you solve a simple Schrödinger equation for just one electron. You see now there is only one position appearing here in this wave function. Then from this wave function, from this single electron wave function, you calculate the density. And from this density, you can actually calculate two guys. One is the so-called Hartree potential, which contains the electron-electron repulsion. They are negatively charged particles, so they will repel each other. And the other guy is the famous exchange correlation potential, which contains all the nasty details of these millions of universes in sort of approximative form. And once you have these guys, you plug them into your Schrödinger equation again, and you solve the whole thing self-consistently until nothing changes anymore. It's of course an approximation, but it's an approximation that turned out to work astonishingly well. So it's nowadays kind of the main workhorse in quantum chemistry, in solid-state theory. Just to give you a flavor, this is a calculation I did some time back. This is a benzene molecule in a magnetic field, and the little arrows show the currents induced there. We use this to calculate the nuclear magnetic resonance shifts of a benzene molecule. So in Mathematica, well, there are two basic ingredients you need for a density functional theory code. You need to be able to solve Schrödinger's equation. This is what I did with finite elements in Mathematica, and well, then you need to calculate these Hartree and exchange correlation potentials, and well, you need to solve the Schrödinger equation. This is what I did with standard Mathematica eigenvalue solver. Now, well, you're probably curious how all of this looks in Mathematica, so let's switch over to Mathematica here. To demonstrate you how density functional theory in Mathematica might look like, I've made a little mock-up research project here. This is a microscopy image of a double quantum dot I found on the internet, and the light things here are electrodes on top of some semiconductor, and you apply a potential here which confines electron to the gray area here, and especially to these two dots. I removed, doesn't work. Sorry, I have to switch here. I've removed all the annotations with an image manipulation program, and then imported the image in Mathematica and did a bit of image manipulation on that image. I turned it into a black and white image using binarize, and then I swapped black and white around, and I also applied this mean filter here to make the edges less jagged and a bit more smooth. So basically, the electrons are free to move in the white area, and the black areas are forbidden. So in the next step, I used finite elements in Mathematica to generate a mesh in the white space. So the result looks like this. Note that up to now, we didn't have to leave our Mathematica notebook. So everything was done within Mathematica. Now, the mesh is, you will notice the mesh is a lot finer in here because this is the area we are actually interested in. And in the next step, well, I removed those wedges here because those wedges are completely disconnected from the rest and they are not needed in the calculation. So this is the actual geometry I did the calculations on. Of course, we need a potential for the electrons here. I mean, this is not real research work. I had to guess a bit. Again, this is very nice in Mathematica, so I tried to come up with a reasonable potential for electrons. You see here, it's a simple Mathematica function. I basically tried it out until the potential and plotted it until the potential looked reasonable. So this is the zoomed out area for those two dots where you have the potential is a bit deeper here and here, but eventually if the electrons have a large enough energy, they can move out of this double dot regime here. Okay, now let's go on to the density functional calculations. This unfortunately looks underwhelmingly simple. As a user interface, there are practically two functions. The one is this setup Konchem, which sets up the initial calculation, and the user gets back basically two things. One is, well, stuff that is fixed during the iterations, and you get back an initial state to start your iterations with. And the actual density functional theory calculation is hidden in this function Konchem iter, which does the Konchem iterations. And you see I started it here with my initial state, and I called it 3 times here with different parameters to try out how it converges. You see it took between, well, a few minutes and then a bit more than 10 minutes, depending on the parameters. And what the user gets back is a list of results for all the Konchem iterations. Again, without leaving the Mathematica Notebook, you can extract interesting information, like this command gets their rows, extracts the difference in consecutive densities in the iteration. So this tells you, does it converge or does it just oscillate back and forth? And you see that the first 2 calculations didn't converge very well, but the third one is best. So let's look at the results of the third one. You can, for instance, extract the density. This is get rho, because rho is the density. You see the electrons are really largely confined to those double dot regime, but a bit of density is spilled out here in the area between the electrodes. Yeah, you can also look, of course, at the so-called Konchem states. Again, for the physicists, I'm aware that Konchem states, or the physical nature of Konchem states, is, well, heavily debated. But my point here is you can extract them from the data. You can use Mathematica's manipulate command to look at the results here. You see that the lowest energy state is confined here, and if you go to the next state, it's here, and if you go further up the energy, you see it quickly gets more complicated, and actually, well, it's a very nice artistic image, I think. So this is, the whole thing is the whole calculation is contained in a CDF file. You could now send off to your colleagues for inspection and for discussion. And, well, I'm reminded that I still have 5 minutes, so let me, 5 minutes more, yeah. I'm sorry. So let me quickly go back. How does it compare to other density functional codes I've used? Well, disclaimer here, comparing these codes is not really fair. They have completely different sets of features, and it's largely anecdotal evidence, and don't consider this to be a benchmark. It's orders of magnitudes matter, but actual numbers not. So I've been part in the development of 3 codes myself. The oldest one is limerick. It was a Fortran code, and my rough estimate is that 3 to 4 person years went into development. And it turned out to be close to 50,000 lines of Fortran code. And, well, to give you a rough comparison how the codes compare feature-wise, I normalized this to say this code is 100% of the features. The next iteration was passed, this C++ code. It covers kind of 80% of what this Fortran code can do. It took 1.5 years to develop, so you see, well, probably a lot of experience from here went into here. Turned out to be 20,000 lines of code. And now the Mathematica code you've just seen, I implemented the finite element stuff myself. So this is probably something you wouldn't do once Mathematica 10 is out, because finite elements are already there. Finite element part turned out to be 860 lines of code, and the actual DFT calculation is 250 lines of Mathematica code. Of course, it doesn't have nearly as much features as the C++ code, maybe not even half of it, but I think lines of code speak a pretty clear language. It's very, very simple. I mean, it took me roughly, well, a few weekends, so say 50 hours to develop it. And, well, I've only did show you 2D calculations, but it can also do 3D, but we are still stuck with importing pseudo-potentials and all that stuff. Of course, you might ask me about speed. Again, very different codes, very different algorithms, so it's very hard to compare. So the gist of it is that Mathematica turns out roughly to be equal to C++. So for one specific problem, I'm really ready to show you numbers. For one specific problem, for a harmonic oscillator, the C++ code turned out to take 4.1 seconds for one Konchem iterations, and Mathematica came in at 4.5 seconds. But it's pure coincidence that it's that close. I mean, you can change just one parameter and runtime changes by a factor of 4. But this is just to tell you it's roughly in the same ballpark efficiency-wise. So let me conclude to make Philip happy. Apart from obviously achieving a lot with very little code, what I really liked is interactive development in a notebook. So you make less mistakes because you can develop something by example, immediately plot it, and if you see a visual representation of, say, your density or your wave functions, it's very easy to spot errors. So, and what I probably liked best is that the final code has much better composability because you don't get a large monolithic code, you get more like a domain-specific language for solving problems in your area. If you want to have a simple picture, the picture I have in mind is from my childhood days, where I really liked Lego, and this is a bit, it's the same thing here. You're given a set of simple bricks, and it's up to you what vastly different things you build out of those bricks. Okay, so that's the end of my conclusion. And are there any questions?